Hello, in this video we will be looking at the continuum hypothesis. So whether we're talking about a gas or a liquid, fluids are a collection of microscopic particles that are spaced out, that move, collide and interact with each other. So if we want to calculate exactly a fluid flow, we should be doing this by calculating the dynamics of each individual particles. For instance, in a cubic centimeter of water, we know that there is about 10 to the 23 particles, which means that this would be a daunting task, pretty much impossible. So we won't do that. The next best thing is statistical mechanics, in particular the Boltzmann transport equation that considers the probability of having a particle at a given point in space and at a given speed, rather than calculating or modeling the particles directly. This is quite a difficult theory, and we will look at it elsewhere, not here. Rather, here we have a powerful tool that will allow us to take shortcuts, and this powerful tool is called the continuum hypothesis. To understand what the continuum hypothesis is, we need to first understand what a fluid is. So as I said, a fluid is a collection of particles. So I'm drawing some particles sort of randomly distributed in space, like this. And these particles all have a velocity. For instance, this one goes in this direction, this one goes in this direction, this is going there, 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 and there. Okay, so this is essentially our fluid, and these are our fluid particles. And what we are going to do with this, essentially, is zooming out. So we're going to zoom out and consider that all this is in a small cube in our domain here. And outside, around this small cube, we're going to draw a larger cube, which is going to be, in a sense, a fluid blob. Okay, so this is our larger cube, which we're going to call delta V. So this larger cube, I'm going to define its size or its edge as D, and it's got volume delta V, and it contains very many fluid particles, as you can see here. So this is called, in the jargon, we can call this a blob of fluid or a fluid particle. And I put particle between quotation marks because these are not particles essentially, right? This is a collection of particles. This is a volume essentially. And then from that volume we can zoom out even more. So I'm just going to draw this small volume of fluid, this blob of fluid, as this tiny little cube here. And if I want to look at my flow, the flow that I'm considering, for instance, the flow within a pipe, so I've got the walls of the pipe here, okay, and this is my velocity, my quadratic velocity profile in my pipe. You can see that this blob of fluid is small compared to the size of the domain, and I'm going to name the size of this domain A, the characteristic size of this domain. So this is essentially our fluid flow, right? So this is microscopic. This is microscopic. And what we're doing here is that we're going from the microscopic to the macroscopic, okay? So the key point here is that instead of working with the fluid particles like we would be doing in the context of a microscopic calculation, what we're going to be doing here is working with these blobs of fluid, but we need to be careful before defining it. So there are two rules. The first of these rules is to take D, the size of our blob of fluid, to be large compared to Lm, and Lm is what I will call the molecular size, okay? And typically Lm is about 1 angstrom, which is approximately 10 to the minus 10 meters, so it's very small. And the reason why we're making this first assumption, or the reason why we have this first rule, is because it allows to have many particles in delta V, many fluid particles in delta V, and the consequence of which is that the fluctuations that are due to the dynamics of individual particles are averaged out in dV, okay, in delta V. So this is the first of these rules. And then the second of these rules, so as you can see, we have a large enough volume, but this volume needs to be small compared to the characteristic lengths of our fluid flows. So D has got to be small compared to A. In a sense, paraphrasing the fact that delta V should be approximately a point in space. Okay? So we have these two rules. The first of these rules essentially tells us that we should have very many particles in our element of fluid, in our fluid particle here. But at the same time that this blob of fluid should be small compared to our domain, okay? So that it can be seen as a point in space. And based on these, we can essentially try to phrase the continuum hypothesis. So the continuum hypothesis goes as follow. Molecular details can be smoothed out by assigning to the sought function at point, so this is a point in space, point P, the average value of this taken by this function in the element delta V centered on P. Okay? So essentially what we are going to do here is take the value of that function for all the particles that are within our blob of fluid. We're going to average all this out, and we're going to say that the velocity, for instance, in that blob of fluid is equal to that averaged value. Okay? And because essentially we're averaging over a large number of particles, what is going to happen is that this function is going to be a smooth function of time and of the position, allowing us to model this domain as a continuum. Okay? So, for example, we can say that the velocity at point P, and that's going to be a function of time, will be equal to the sum over all the particles in delta V of the velocity of the particles. And this is a function of time, of course. And that will be giving us the sum. So what we need to divide is essentially by the number of particles in delta V. So that's going to be the sum over the particles in delta V of 1. Okay? So that will be defining our velocity. We can also define very many other quantities in this fashion. For instance, the density rho at point P, which depends on time, can be essentially defined as follows. It can be the sum over all the particles in delta V of the mass of each individual particles. I'm going to assume that the mass of the particle does not depend on time. That's the mass of the particle. And we have to divide this, obviously, by the volume, which is delta V. Okay? So, and of course, there can be a change in the count of particles within delta V. Therefore, this temporal dependence here might come from the number of particles coming in delta V. So this sum is not in a fixed number of elements. And as you can see then here, these definitions, because of the property of the continuum hypothesis, essentially zooming out so that we have very many particles in there, making this essentially a continuum, or making it approximable by a continuum, gives us the fact that these functions are smooth functions of time and position. At least that's what the hypothesis tells us. Okay? And therefore they're differentiable functions. Alright, so in this video we've seen what the continuum hypothesis was. We've seen that we could essentially take a microscopic collection of particles, that is to say a fluid, zoom out, and from zooming out provide a mathematical framework that allows us to model the fluid particles, to model the fluid flow as a continuum. This concludes this video on the continuum hypothesis.